Okay, so for today's lecture, I will continue on the AC analysis, okay, mid-frequency, part 3 still. Like I said, we have 3 parts, okay, for the AC analysis. It will be the common emitter, okay, common collector, and also common base. Okay, so for common emitter, you have two circuit configuration. Okay, for the bypass RE, emitter resistor, and unbypass RE. So unbypass RE is quite complicated because you have to derive the input impedance at the base, okay, and also the R out. Okay, so and then common collector and common base. So today we will look through the common collector and common base. Okay. Right. So today I plan to do the derivation. Okay, and then after that, after I derive, after that I will go on the example. Okay, so this is just a recall. Okay, to analyze the circuit, you need to have the DC values. Okay, in order to find the Q points. So Q points needed here is the collector current IC. Okay, and then if you want to draw, then step number 2 will be your starting point to draw the equivalent circuit, the AC equivalent circuit. Okay, what did you do? You have to replace the DC power supply, become short circuited. Okay, and then you will replace the DC current source with open circuit and ground it. Okay, and then what happened to the capacitor? During DC analysis, capacitor open circuit, but during AC analysis, capacitor short circuit. Okay, and then you will replace the BJT itself to the hybrid pi model. Okay, so hybrid pi model, it has certain parameter. So this parameter, you need to memorize it. You have R pi equal to GM V pi. However, in order to find GM, you need to have your IC value. So GM is equal to IC over VT. Okay, and then if there is VA given in the question, you might have to find the R naught. So R naught is the internal resistance of the hybrid pi model, okay, which is equal to the VA over IC. Okay, fixed value of VA is 200 volt. But if only the question said that VA is infinity, therefore you can neglect your R naught. Okay, you don't have to draw your R naught because it become open circuit and it is too large due to the infinite value VA voltage. Okay. All right, so this is the hybrid pi model. Okay, so actually you're gonna have R naught here. If R naught is given, VA is given, so you have R pi, GM V pi, and R naught. Okay, so and then at the back here, okay, from base to emitter, you have to draw from point to point all resistor exists in the circuit here. Okay, all right, so this is what we have done. Okay, so this is for the common emitter bypass RE. Why bypass RE? Because in the question given capacitor and emitter. Therefore, during AC equivalent circuit, capacitor is short circuit. Therefore, RE also short circuit. In the AC equivalent circuit, there will be no RE here. Okay, so this is what we call as a bypass RE. Okay. And then we derive the input impedance and also we derive the output impedance. All right. Okay. And then after that, we find the gain, voltage gain. Okay. Without RL, which is AVOC. So you will get this, okay, which is equal to the V out, V in. So V out is voltage across the resistor here. Okay, which means if it is straightforward, so it's like RL parallel with Z out. Okay, and then sorry, RC, this is without RL. So why negative? Why we took negative? So the current source here, is going down. Okay, in order to get positive V out, it's like the current source is going to the opposite direction. That's why we have to take the negative sign here. So negative GMV5 times the total resistor that you see from the output here. Okay, since we are calculating the AVOC with the RL, so you don't have to include your RL in the equation here. Okay, therefore the AVOC equal to negative GM times R naught parallel with RC. And then you have to find the AV, V out over V in, and so on. The same method, but now with RL. And then later after that, we derive on the voltage gain referring to the source, which is equal to the V out over Vs and so on lah. So this is, I think you have familiar with this. All right. Okay, and then you have to derive also the current gain, which is I out over I in. So make use of the output equivalent circuit where AVOC V in, Z out RL. So this is from the amplifier model that we have learned in the previous, in the beginning of this chapter. All right, so use this, make use of this circuit, and then you find I out using KVL here, and then I in using the input circuit where you do the voltage to current source transformation. So you will get like this and so on. Okay. So we've done the example one. And then I asked you to do the exercise one, this one, and submit it to um, the Padlet. Okay, so this one will be short circuit. So this is actually bypass because CE is short circuit. So this is short. Okay, so at collector you have RC, and then you have RL, and then after that from that RC2 you have RC1 to the ground. Okay, so actually you have 3 resistor at collector. Okay, one RC here to the RL and then RC to the ground. Okay, I want to see your answer first before I give the solution here. Okay, all right. So this is done. Okay, so for the unbypass, okay, let's take a look on the unbypass. So unbypass is quite complicated because you have RE here. Okay, you have RE and you don't have capacitor. So you need to include your RE here. Okay, so in order to analyze this, in order to find the Z in is not straight away RB parallel with R pi plus RE. If you do that, then it will be wrong. Okay, you need to find the input impedance from the base to the ground where we call it as a Z in B. Okay, how to find the Z in B? You need to do the total voltage from the base to the ground. VT is equal to the V pi series plus VE. Okay, VE. So VE is equal to the IERE, V pi, IB, R pi, because current going into the R pi is at the base, which is IB. Okay, so if you notice here in DC analysis, usually you will write the capital letter IB and capital letter IE. But in SC analysis, most of the time, I think in the textbook also, they use that small letter. Okay, small letter IB and IE. All right. So and then IE replaced with that one, this one. So you will get the equivalent ZIB is equal to R pi plus beta plus 1 RE. And then Z in is equal to the RB parallel with ZIB. Okay, that's it. So this is the derivation that you got. Okay. And then after that, we find the the AVOC. So for this AVOC, so you see that AVOC is V out over V in. Okay, V out over V in. So V out, okay, V out is quite straightforward because V out is equal to the voltage across resistor RC. Again, that your GMV pi is going downward. So in order to get positive V out, you need to have current going downward to your RC. So it's like opposite direction. So you need to put negative GMV pi RC. Okay. And then how about the V in? So since I have derived this, so this will be easier for you later because V in is equal to the VT, V total. Okay, V in is equal to the voltage across RB as well as voltage total from base to the ground. Okay, it is in parallel. So you have got the values here. Okay, I mean the equation here. So you just plug in. And then you simplify it. Finally, you get AVOC negative GMRC over 1 plus GMRE. All right. And then find the current gain, I naught over IE. Okay, so you do the transistor, this not transistor, this is the amplifier model simplification. So the voltage amplifier model, so AVOC Z out RL, so I out is KVL across this loop. Okay, and then you get this. Okay, and then the input will become voltage to current source transformation. Okay, so you have IS, blah, 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 like this. And then, so this is to find IIS. Okay, I in is equal to, what will be the I in? So I in is equal to the, so this is actually the, where you simplify, V in equal to I in over Z, I in Z in. Therefore, you take out from right to the left, I naught over I in, you get the AVOC Z in Z naught over RL. Okay, so please concentrate on the BJT. So it is quite long calculation from the DC to the AC part. So for your information, for your task 2 later, only BJT topic. Okay, from DC to AC analysis. So we have not finished yet. So the one that we have done in the previous class and today is just for the common emitter. Today we need to derive for the common collector as well as common base, right? Okay, so last time I did not explain yet. Okay, so yeah, I said that Z out is finally equivalent to the RC, but there is a behind the scene how this Z out is equal to the RC. So by using imaginary voltage source. Okay, so I need to explain this, I need to derive this. Okay, in order, I think this is good for your understanding. Okay, although in the end of the day you will get that Z out is approximately equal to the RC, but the concept how they get Z out is equivalent to RC, I need to explain it to you lah. Okay, so okay, so can you see my slide, student? Hello?
Yes, doctor.
All right. Okay.
Doctor.
Yes. Yes, Manta?
Yes, I'm saying yes, we can say.
All right. Okay. 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 To determine Z out is by using, we call it as a imaginary voltage source. Okay, later I will upload the slide. Okay, so actually, okay, as you can see here at the Z out, so as you can see that Z out is actually here. Okay, so sorry to use different color. So Z out is actually is equal to the RC, and there is a resistor input there is the output resistance here, output impedance here, where we call it the Z test. Actually, there is a impedance at this side. Okay, we call it as a Z test. Okay, same goes to this one. There is a resistance total impedance at this node. We call it as ZIBs. Same goes to the at the output at the collector. We call it as a Z test. Okay. So now let's find what is Z test. Okay. Although in the end of the day you get that Z out equivalent to RC, but then let's find out. Let's see how they find the Z test. Okay. So actually Z out is equal to the RC parallel with the Z test. Okay. So Z test is how to find Z test is by introducing we called it as voltage imaginary. Okay, voltage imaginary here we call it as a V test. Okay, V test. right, V-test. Okay, so let's see the equivalent circuit here. Okay, for example, if you have R naught, let's see, there is R naught here. Okay, so we draw it here. Okay, let's see if R naught is given. So this part will be your GMV pi. Okay, okay, and then if let's say we put the ideal case where there is a R naught. Okay, and then here you have RE. So why this become complicated? Because we have RE over there. Then that's why we need to do the Z test, okay, voltage imaginary. And then that after that at RE, you have also the R pi at the input. And also for this case, okay, for this case, you have RB. Okay, and then I say we inject voltage imaginary, which is V-test. Okay, so this is the equivalent circuit. Okay, so now your objective is to find this Z test. Okay, Z test. So when you have imaginary voltage V test, then you have the I test, which is going out from the current source V test. Okay, I test. So what would be the Z test would be? So it would be V test over I test. Okay, so now let's find how to get V-test and I-test. Okay, so for example here, as a note, so imaginary voltage test, okay, only can be added, okay, when there is an independent source, okay, which is used that particular circuit lah. I mean at the input source, when you have current source, then you can only inject the V-test. Okay, so let's let's transform this circuit. Okay, for example, so this is your base. So this is, am I drawing the right one? No, sorry. So RE is here. Okay, so RE is there. Okay, so this is emitter. So this is collector. Okay, so let's see the equivalent circuit here. Okay, so the equivalent circuit will be, okay, so let's say if I draw it in this side. Okay, give me 1 second. All right, so if you have V test over there, okay, okay, so this is your V test. Okay, and then if I want to draw the circuit is upside down like this. Okay, so this is, okay, so you have V test and then you have arrow going down. So you have V test and then you have arrow GMV pi here. Okay, I want to do like this, drawing like this, because easier for you to look at what I'm talking about. Okay, and then in parallel with GMV pi, you have R naught. Okay, R naught. Okay, and then after that at R naught, okay, R naught here, after that, so this point and this point, GMV pi and R naught, you have RE to the ground. Okay, RE to the ground. Okay, the same point negative for the V test. So this is your RE. Oh, okay. Sorry. Okay, you have RE and then you have, after that, after you at the point of RE, you have, so this is plus minus V pi, and then you at the point of RE, you have R pi. Okay, and then R pi straight away connect to the RB, which is in series. You have here RB. Okay, so this is R pi. okay, where this point RE is connected to the negative V pi here. So this is negative first, and then this is plus V pi. Okay, so it's just I transform it this way. Okay, easier for you to look. It's just that I take this. So sorry. Okay, so just I take this two. Okay, instead of in vertical, I draw it in horizontal like this. See, it is just the same thing. Okay, I redraw it so for better understanding lah. Okay, so don't forget put everything here. So you have I test. All right. So for example, at this point, you have this is current source, GMV pi. So here, okay, at this point, what will be the current? So if we do KCL here, student, so current at R naught will be what? So current at R naught will be?
Short circuit.
No. So we do KCL, current going
Negative.
in. Current going in equal to current going out from this particular node. So what will be the current at R naught here? So you have I test going in, and you also have I out going here, which GMV pi, and so this current will be
I test or like
Terminal GMV pi.
yes, I test minus GMV pi. All right, so that will be the current there. Okay, and then when you have current going in here is I test, therefore current going out here is also equal to the I test. All right. Okay, so that's it. Okay, so let's derive it. Okay, so in here, if you do, so for example, I write it here. So what will be your V test? Okay, okay. So V test is like you apply KVL in this loop. Okay, you apply KVL across this loop. Okay, that will be to find the V test lah. Okay, to find the V test, right? So since that this resistor, okay, these two resistor, you know that RB is very, very large, usually mega, okay, RE is more like 1K, okay, most of the time when we design the circuit, okay, RB is very large and you get IB is very, very small, approximately 2 micron, right? If you still remember, student, okay, microampere for the IB.
Yes.
Yes, okay. So at this node, okay, this current I test, and since this current we assume that very, very small, therefore we can assume that, okay, since I test is at collector, RE, this is IE, so we can assume that this point, the current also equivalent to the I test. Okay, I test. All right. So V test will be, so V test is equal to the voltage across R naught. Okay, voltage across R naught is equal to the current I test minus GM V pi. Okay, R naught. Okay, what are the else the voltage? So you have this resistor and also voltage at RE. Okay, which is equal to plus I test RE. Okay, okay, only that. So the V test is equal to the I test minus GMV phi R naught plus I test RE. So that is one. Okay, one thing. Okay, not finished yet. Okay, so what else? So let's say I put this current is I. Okay, I. Okay, let's by using current divider rule. So what will be the I? So I will be, so since I said current I across this R pi, okay, I just put it I. Okay, so current I here is equal to the, by using CDR, is equal to the RE over RE plus uh, R pi plus RB, okay, times I test. Okay, time I test. Okay, So that's it. All right. This is times. Okay, so you have two parameter here, two component lah. Why I did that, so that later for the equivalent circuit you'll be much clearer. Okay, so I need new page. Can you all wait? Before that, I forgot to save. Oh, I forgot to save just now. Oh, sorry, student. I forgot to save just now. Oh my god. Oh my god. I need to draw again. Sorry. Okay, doesn't matter. I will draw again later. Okay, but now I will continue where I stopped just now. Okay, I think I can recall everything. Okay, so I will for the slide that I have I forgot to save just now. So just make a I will write again later before I upload, but I'm not going to draw it again. Okay, so uh okay. All right. So V-test, sorry, V-test. Where did I stop? Okay, V-test. I need to draw again. Kalau tak, you tak nampak. Okay, so you have V-test over here. And then you have I-test over here. And then I said this is GMV pi. So this is R naught. So the current flowing here is equal to the I-test. Okay, minus GMV pi. Okay, so you have RE over here. So current here approximate equally to I test. Okay, and then I say I find current here. This is R pi, this is RB, and minus plus V pi. Okay. Oh my God. Sorry, guys. All right. So, what's this? Okay, so your friend said R pi and RE in series. R pi and RE in series. RE? No, not in series. Not in series. Okay, so it's a different note over there. Okay, so yeah. Okay, so and then find. All right, so that's it. Okay, we write again. So I said V-test. Okay, V-test is equal to the okay, that loop. Okay, I test minus GMV pi R naught. Okay, plus I test RE. Okay, and then I want to find current by using CBR pula lah. Okay, current is equal to the RE over RE plus R pi plus RB present. That is not in series. Okay, same like when you solve the ZIB. Okay, so R pi and RE not in series. Okay, it's a different node. One at base node, one at emitter node. Cannot be series. Okay, times I test. Okay, that's it. Okay, so now, okay, there you go. My new one. So V pi. Okay, V pi here is equal to the negative I R pi. So I just create an imaginary current here, I. So V pi is equal to negative because there is negative V pi, negative node here. Okay, negative node. Okay, if I say it like this, so negative V pi is equal to I R pi. Okay, I take the volt current negative there and put it here. Okay, therefore V pi equal to negative R pi. So here V pi is equal to put everything here where you have already the current portion here I. Therefore I here is equal to negative, put negative, and then you have RE, okay, over RE plus R pi plus RB, okay, and then you have here R pi, okay, because it's times R pi here. Okay, sorry. So this is I test and R pi. Okay, all right, R pi, like that. Okay, so take again your V test over here. Okay, your V test over here, you write again. Okay, so V test will be equal to, okay, I test R naught. Okay, I expand the equation. So it is equal to the I test R naught. Okay, and then minus GM R naught. Okay, GM R naught. All right, and then plus I test RE. Okay. So you need to put everything, the equation, the I test that you have get just now. Okay. So you have here oh sorry. Alamak. Hello. Ingat kelas lah. Ingat kelas. Okay, bye. Hello? Hello pula. Guys, sorry. Okay, so V test is equal to the I test R naught minus GM R naught, and then it is equal GM R naught plus I test RE. So GM V pi R naught. Sorry, I forgot to put GM V pi R naught here. Okay, so it is equal to the GM V pi R naught. Okay, so now you put everything here. Okay, so the GM V pi, you have the equation here. GM V pi. So and then you put the GM V pi. Finally, you will get that your V test, okay, your V test is, if you simplify the equation, you will get V test is equal to the I test, okay, big bracket. So you have R naught here plus GM R naught, RE R pi, okay, over RE plus R pi plus RB, okay, plus RE. Okay, so you get that. So now, okay, I said that Z test just now. So this is your Z test just now. So Z test is actually equal to the V test over. Okay, need to save it here. Okay. One more slide because too much derivation. Okay. Therefore, you got that your Z test, okay, Z test is equal to the V test over I test. Okay, you take everything from here. Okay, I cancel this. Okay, you take everything from here, from the I test, you bring from the left to the right. Okay, so your friend, madam, may I ask why the I test is not divided into RE and V pi, and current across RE is I test? So I have explained just now why current I test is not divided into RE and V pi. Oh, okay. So I want to simplify my equation. So here is collector, Peng Ang. Okay, so this is collector, this is emitter, this is the base. Okay. All right. So current at the base here, I put it as I. So but actually current I here is too small lah, because usually current at resistor RB is very large. Okay, RB is very large. Usually mega. If you remember, most of the question, if we design the common emitter, RB will be very large. Okay, compared to the RE. Okay, in this case, okay, we assume that, okay, because I want to simplify everything, so I assume that this I test, okay, will go to this path only because the RE is just 1K or 2K instead of RB mega ohm. Okay, so I assume that if you do the current divider, so current at RE is approximately equal to the I test. Okay, I test will not go to the large resistivity at RB, it will only go to the RE. Therefore, I said approximately equal. Not equal, but I assume approximately equal to the I test. Okay. Alright, so apa tadi? Why just now? Oh, okay, okay. So V test over I test, okay, is equal to this one, okay, which is R naught, okay, all the portion over there here, this one, okay, the R naught plus GM R naught, RE, R pi over RE, okay, plus R pi plus RB. Wow, too long the equation. I hope you are hanging there, student. Okay, so done. Okay, so Z test V test is equal to that portion. Okay, so this portion, okay, this portion, okay, so this portion is actually very large lah. If you so this portion of Z test is very large value. Okay, large value. Okay, so if we calculate the Z test, plug in all the equation, you will get that Z test is very, very large than RC. Okay, so look at here. So I said that in the previous slide, which I have deleted just now, accidentally deleted it. Okay, so it is actually okay. So it is actually, so this is your Z test. Sorry, student. So this is Z test. Okay, Z test here. So Z out is actually equal to the RC parallel with Z test. Okay, so in here, since it is very large, therefore Z out is equal to the Z test, okay, parallel with RC. Since Z test is very, very large, if you do parallel thing, 1 divided by Z test very large, so you will get a small value approximately equal to 0. Finally, that's why Z naught is equivalent to the RC. Okay, with this one, which I haven't derived in the last class. I just said that Z naught is equivalent to the RC, but how it get equivalent to the RC is by using injecting imaginary voltage, which is V test, which is I have deleted here. I will write it again before I upload. Okay, and here. Okay, so that's how you get the Z out is equivalent to the RC. Okay, that's it. So this is for AVOC. I have explained the previous class. So this is AI. So so your friend asked me in the chat box. Let me read. Okay, wait. Okay, so okay, base current is small, so assume I test only across RE. Correct, Peng Ang. Okay, so Muhammad Ali asked, why is the polarity of V pi is inverse? Okay, so from here, which is I have deleted. So Muhammad Ali, so carefully look what I'm explaining now. Not only Muhammad Ali, everyone. Okay, why is it inverse? Okay, so now this actually not inverse. This is actually I am rotating it. Instead of it is vertical like this, I'm rotating it become horizontal. Okay, as you can see here. So this is your arrow of GMV pi going down. If I make it horizontal, it will go to the left. Okay, to the left. Okay, so this arrow of going down here will meet the RE. Okay, it will meet your RE here. Okay, but I want to make it this RE going to the ground, of course, like this. And the other side of RE, okay, is connected to negative V pi here, negative V pi. Okay, and then that's why this R pi will go upside down. So negative will be upward, positive will be downward. So I'm drawing it upside down like this. So this RE connect to the negative and positive go to the RB. Okay, positive go to the RB here. All right, are you clear, Mama Ali? Okay,
Yes,
Mitai?
ma'am. Thank
All
you.
right, great. Okay, that's it. Okay, so this is the derivation. So I'm happy that I have derived it. I've explained it to you so that yeah. So we inject the imaginary voltage. Okay, I will write it again here, which I haven't saved it just now. So yeah, that's why finally we get the Z naught over RC. So so you know why Z naught is equivalent to the RC. So I hope you understand it. Okay. But finally, don't derive to the Z naught, the V test I test in the test. Okay, because finally you can always say that Z naught is equivalent to the RC. Okay. All right, so we've done this, student. Okay, actually they have the explanation here, better drawing here. Okay, same like I have drawn just now. Okay, but better. Okay, so I'm not going to try this example. Okay, but because I want to derive the common collector. Okay, next is the common collector. Okay, so for the common collector, so like I said, common emitter where you have resistor emitter at the ground. Okay, here. Okay, but for the common collector, you have collector now. So this is your base. Okay, this is your emitter. Now collector, as you can see, to the ground. So this is what it meant by the common collector. Okay. Still, you're gonna have so the circuit here looks like so collector to the ground. Okay, to the ground, which is the VCC. So the GMV pi here straight to the ground. Okay, so this is how the circuit will be. Okay, so let's see how the derivation. Okay, so we are taking this circuit, okay, and we want to draw the equivalent circuit here. Okay, actually there is here, but it's okay. I want to derive it so that you'll be much clearer. Oh, okay. Mm-hmm. All right. So you have the circuit over here from collector. I need to copy this circuit for a while, okay, so that you can see. Okay, over there. Okay, so you have there the circuit. Okay, what happened to the power supply will go to the ground. Okay, what happened to the capacitor? It will be short circuit, capacitor short circuit. Okay, so now first thing is to draw your AC equivalent circuit. Okay, AC equivalent circuit. So you have here so you have R pi. Draw your hybrid pi model. So you have R pi. Okay, and then here RC you have you have here a base. Okay, okay, at base and emitter you have V pi. Okay, and then at emitter you have RE. Okay, and then here you have GMV pi. Okay, so where does the GMV pi goes? To the ground. Okay, it will go straight to the ground. Okay, ground. Okay, ground. Okay, and then RE you have um ground. Okay, and then at the base you have RB. Okay, RB. Okay, and then here at the base, here you have RB to the ground. Okay, RB to the ground. Okay, and then this is your P in lah. Okay. Okay, and then don't forget to put your Z in. So Z in is seeing from here. Therefore, this is your Z in. Okay, Z out is where you see at emitter. Now, here, this is your Z out. Very different from the common emitter. Okay, so this is how it looks like. Okay, the circuit, the AC equivalent circuit for common collector. Okay, for common collector. Okay, so let's us derive together. Okay, so again, what can you see? What are the similarity in this common emitter at the input here? Okay, at the input here, student. Okay, what are the similarity with the common emitter unbypassed just now? So it is the Z in, right? Right? Why I said that? Because at this point from base to ground, you have the parameter apa? What parameter here? You have Alex? So Z in is equal to apa? What? Z in is equal to RB parallel with something. What is that something, Alex? Same like common emitter bypass just now.
Same like
Same,
that.
right? So what are the parameter here, Alex?
R
From here,
I RB in
yeah, yes, this one. So you have here is Z I.
IB.
Yes, thank you. ZIB. So Z in is equal to the RB parallel with ZIB. Okay, so how you find the ZIB? Same like what you have done in the previous one. Okay, in the this one. Okay, where you need to find the V total across base to the emitter. And then ZIB is equal to the V total over IB. Okay, you need to find this V total. Okay, same thing. It is the same thing. Okay, so it is the same thing. Okay, that's why I derive it at the beginning there. Okay, so that later after on you can see the similarity. Okay, so ZIB is equal to the VT over IB. Sorry, VT over IB. Okay, so now what is VT? So VT is equal to the, okay, VT is equal to the V pi plus IE RE. So this one is IB R pi plus beta plus 1 IB RE. Okay, so VT is equal to the IB R pi plus beta plus 1 RE. Okay, if you take out there, therefore, you get that Z in B. Okay, this is VT. This is VT. Therefore, Z in B is equal to the VT over IB equal to the R pi plus beta plus 1 RE. Okay, see, if you do a lot of derivation exercise, you will be much faster lah. Okay, all right, so that's it. Okay, so Z in is equal to the RB parallel with ZIB. Okay, so now, how to find the Z out? So do you have any idea how to find the Z out? Student? Okay, so I use,
Equal to RE or what?
sorry, okay, yeah, okay, it can equal to RE, but then there is a way to do it lah, basically by injecting the again the imaginary voltage. Okay, so we inject the imaginary voltage, so I need to you. So how they get the voltage and okay, so draw here. So this one. So why is it important? Because okay, like in here, so to find the Z out, actually we will replace this RE, okay, with V test. Okay, so if I draw it again here, so you will get so it's like you inject sorry okay, so if I draw it here again, so the circuit will be macam ni. Okay, to find Z out, we inject imaginary voltage test at RE. Okay, therefore this circuit will be, so you have here R pi, I draw it again, okay, V pi, okay, and then you have here is GMV pi, okay, and then you have ground here, and then here instead of RE you have here is V test, okay, V test, right? So why is it like this? Okay, this is what we call it as the imaginary injection voltage. Okay, so at this node actually you have your RE. Okay, your RE. So now you are finding your Z test over here. Okay, and from here is Z naught. As you can see, Z naught is from the, you are seeing the Z naught before after RE. Okay, so actually Z naught here is equal to what? Z naught is equal to the RE parallel with Z test. But the problem is, what is Z test? So the same method like I have explained in just now, okay, the same method where you do the V test, I test. So you need to find what is the V test and I test. So since this is going down, so this is your I test. Okay, so this is your I test. Okay. Okay, this is the eye test. So you know that this is your IB. Okay, and then that's it. Okay, all right. So now is equal to the eye test is equal to the, okay, so eye test is going down there. So eye test is equal to what? If you do KCL at this node, student. So I test is equal to what? So I test is going down here. So at this node, I test equal to what? You have IB and GMV pi going in. So I test equal to?
IB plus GMB pi.
Yes, IB plus GMV pi. So this is collector. Okay, so IB plus GMV pi. Okay, so if you actually derive it, so you know V pi is equal to the IVR pi. So if you can see here, so GMV pi is at collector, right? At collector. So this is base. So the current going there is base. So GMV pi is actually equivalent to what? Because this is at collector.
IC.
GMV pi, correct. It is equal to the IC. Okay, IC, right? So if I write it here, okay, IB plus IC, okay, so IB plus beta IB, if you still remember that, okay, so it is actually equal to the beta plus 1 IB. Okay, so what are the resemblance here? So I test is actually equal to what? This equation looks like what? Looks like equal to the IE,
VE.
right? Okay, so V test now. So V test is equal to the, okay, what is V test? How to find V test? In the last slide, how do I find V test here?
I test.
Uh, here. So how did I find V test? This one. Macam mana I cari V test? How? By using?
KVL.
Yes, KVL at that yellow loop there. So same goes to here. In order to find the equation for V-test, you need to do the KVL loop here. Okay, KVL loop over here. Okay, okay, like this. Okay, so V-test here is equal to the, can someone? Equal to what? V-test? Just KVL loop. So it is equal to the, am I dreaming? This is RB. Okay, so equal to what? So current here is the same current. There is no point there. So therefore this is the same current IB. Therefore V test is equal to the IBRB plus IB R pi, or this is actually P pi lah, same thing. So I straight away put equal to the IB R pi. So V test is equal to the IB RB plus R pi. Okay, so V test is equal to the IV RV plus R pi. Okay, so I test you have this value, which is beta plus 1 IB. So you put the equation there. So IB, right? So now you will get that this equation will be V test over I test. Okay, V test you has IV RB plus R pi. Okay, I test also you already have it here, which is beta plus 1 IB cancel out. So finally Z test, which is equal to the V test over I test. Oh my God. Okay, equals to the RB plus R pi over beta plus 1. Okay, so in this case, okay, for this case, actually, if the value is large, actually, but you cannot say it is approximately equal to the RC just now. So Z naught here. So if you can see the Z naught here, this one. Okay, so equal to the RE parallel with Z test. Sometimes Z test, sometimes the you cannot actually say that Z naught is approximately equal to RE. Cannot, okay? It's because Z test in this case common collector is not as large as an Z test in the common emitter and bypass. Okay, so you cannot ignore this. Okay, so you have to use this as well. So but for me, okay, for me, the Z test for common collector is much simpler, okay, as compared to the Z test at common emitter and bypass just now. Okay, you can derive it, or if you don't want to derive it, you can memorize for the Z test in common collector. But then finally, the Z out here, you need to parallel with the Z test. So RE parallel with Z test. Okay. So in this case, so you will have, you already derive it. So Z naught is equal to the RE parallel with Z test. Okay. How do you get the Z test? Is this one. Okay. Okay, now we after we derive the input impedance and so on, usually we will derive for the voltage gain and as well as the current gain, right? If you still remember. Okay, so yeah. Hello? Again? So why do we need to inject? So your friend said, okay, why do we need to inject the imaginary voltage? Yes, we need to inject the imaginary voltage unless you only have current source over here. Okay, current source over here. How you going to find the resistor and so on? So we need to actually, if you do lab in real lab, you put imaginary voltage with any voltage like 3 volt, no sorry, 10 volt or 12 volt. Okay, so in this original circuit, only current source. There is no voltage source. Okay, we need to apply or to inject V test voltage in order to find the impedance. Okay. All right, we haven't finished yet. Okay, so now we just derive for the Z in and Z out. Okay, let's take a look for the AV. Okay, AV and AVOC. Okay, so for the AV, okay, for the AV, okay, I want to use different color. Okay, okay, for the AV is equal to the V out over V in. Okay, where does the V out? As you can see, V out here at that collector. Okay, so V out is actually voltage across. Can I say V out voltage across RE? Student?
Yes.
Yes. Okay, yes. Okay. All right. So V out is equal to the AV equal to the, so I want to find the AVOC since there is no RL. Okay, so AVOC equal to the V out over V in. Okay, now what is V out?
IERE.
Correct, IERE. Okay, betul. See, so why do we insert? Oh, I already answered that. Okay, so IERE. So your friend said IERE. So now that is in DC. Okay, but in AC, okay. So this GMV pi is at collector. IC is equivalent to the IC. Okay, then you know that at RE here, this is IE, where IE is approximately equal to IC. Am I right? During DC analysis, right?
Yes,
Yes, right.
yes.
Yes.
Okay, yes, right. Okay, so the current here is approximately equal to IC. So it is current going down. Okay, this is not negative now, not negative. So current going down means it is going down here. So therefore it is positive, positive IE times RE. Now IE is approximately equal to IC, and IC in this AC equivalent circuit is equal to GM V pi. Okay, are you clear on the V naught?
Yes.
Yes, okay. So now for the V in, okay, V in. Okay, let's take a look V in. So V in is from this node. Oh my, sorry. Okay, so V in is from this node, okay, to here. So what will be the V in? Please look carefully. What will be the V in? Please recall what you have learned so far. So V in equal to what, student?
BT.
Yes, V in equal to the VT. Okay, so V in is equal to the VT equals to what? Equals to, here, my dear student, I have written it here. Okay, so it is equal to the VT, V pi plus,
IERE.
yes, IERE, which is equal to the IERE. Okay, here. Okay. So in here, GMV pi RE is equal to the, okay, in this case, so we may take out, so for this case, I want to actually cancel all the GMV pi, okay, so IE here is approximately equal to the IC, and IC is equal to the GMV pi, therefore I replace IE, GMV pi RE, like that. Okay, so finally you will get, if you cancel out all the V pi, therefore AVOC is equal to the GM RE over 1 plus GM RE. So in the textbook, okay, they write the same thing. Nasib baik sama. I thought luckily sama. Okay, so they got the same thing here, GMRE. Okay, so how they get this is actually this one. Okay, this one, which is I have derived it here. Okay, do you have any question regarding this, student? Before I move forward on the current gain, this is just the voltage gain only.
No, that's not yet.
Not yet. Okay, all right. Okay. So this is for the common collector, okay, for the common collector, and that is for the AVOC. Okay, so now we want to derive for the voltage gain, current gain, okay, for the current gain. Okay, so you have here your okay, I in. Okay, now where is I out? Where is I out? Okay, so as you can see from the circuit itself, okay, from the circuit itself here, okay, this is common collector circuit. This is input, right? V in, of course, when V in connected to the base, so base is the input, okay, and now collector become ground. Where is the output? So output is actually at the ammeter. So as you can see, they have already written here the I naught. Okay, the I naught here. Okay, so therefore, if you write it here, so I naught is here. Okay, so let's derive for the current gain. So for the current gain, you know that AI is equal to I out over I in. Okay, I out is there. Okay, and I in is at the input. Okay, what will be your I out? Student, please take a look there. What will be your I out, student?
Negative GMV5.
Yes, thank you. Correct. Means you are concentrate what I'm saying just now. Thank you. Okay, so yeah, at least someone follow me. Okay, so I out is here. Okay, so I out is going up. Okay, from the circuit itself, it is going up. Okay, going up. Okay, I have written here the clue over there. That's why I put different color here. So this is the IE, different direction. Okay, the same current at the same resistor but different direction. Therefore, we can say that I out is equal to the negative GM V pi. Okay, I out is equal to the negative IE. Okay, negative IE, and IE is approximately equal to IC. Therefore, I out is equal to negative GM V pi. Okay, not finished yet. Okay, what is I in? Okay, how can you get I in? Okay, from the from the past class, how do I get I in? What did I do, student? Usually current divider rule, right? Still remember?
Yes, the
Yes, okay. So if I want to draw again the circuit, okay, at this part, okay, at this input part, okay, so I have here RB, okay, to find I in, I draw again here. Okay, so you have RB. Okay, and then at RB over there, after RB, I don't want to draw the R pi, blah, 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 like that. I want to just to draw the Z in B. Okay, Z in B. Okay, so Z in B here at the base, you know the current here is IB. Okay, and then what else? At RB, nothing else, but you need to put your I in. Okay. I in. So how do you find your I in over here, student? Sorry, I out pula I tulis. I in. How do you find I in? So I give you clue. Find CDR rule first. Okay, find IB by using what? CDR. So IB is equal to the RB over RB plus Z in B times I in. Okay, therefore you have your I in is equal to blah, 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 that portion lah. Okay? Right. So now, if we write it again over here, okay, so your I out will be negative GM V pi, GM V pi, okay? And you know that V pi is IBR pi, okay? Therefore, you can replace this IB, okay? So therefore, it is equal to negative GMR pi, and IB is equal to the RB over RB plus Z in B, I in, okay? Finally, you will get that I out over I in, which is equal to the AI equal to the negative GM R pi RB over RB plus ZNB. Okay, so that's how you derive for the current gain. Okay, do you have any question regarding this for the current gain? I think voltage gain is simpler. Okay, how about the current gain? Do you have any question?
Oh, Doctor, all is
No.
clear.
Okay, great. Okay, because I have explained very clear on the common emitter. I hope the for the common collector you get it. Okay. All right. So we take 5. Okay. So I have terlambat pula. Okay. We usually 1 hour after class I take 5. So now take 5 first, student. Okay. Okay. Well, take 5. Okay. Let us talk about test. Okay. So Chang Yuan Li said negative IE. What do you mean by negative IE? Negative IE?
He answered for the IB.
For just now answer. Huh? For just now answer. Oh, okay. I have answered, right? Yuan Li? Okay. All right. Okay. Okay. For the test, just want to okay. So I will give you the instruction. So test will be started at 9. So let me show you again. So as you can see, test will be at 9:15. Okay, fill up and everything. So I want you, everyone come in at 9. Okay, why at 9? Because I want to delay. I don't want to delay the time later. So I want sharp at 9:25 to download the part A and everything. Okay, so just at 9, everyone comes in to the Webex. Okay. Okay, so this is how it goes. Okay, the test would be, so everything I will do Google form. Okay, we will not be doing the e-learning. I'm afraid e-learning got problem. I don't want that. Okay, sometimes e-learning problem I don't want. So I want to do by using Google Form lah. Is this much simpler for you to actually submit and do everything. Okay, so you will download the part A first. Okay, and then so this is the flow. You will download the part A first, and then you attempt part A. Okay, everything you submit on the Google Form. I will prepare the link and the instructions. So maybe I will post out by today afternoon. Okay, the step. Okay, I mean the flow. Okay, I will including the link. Okay, including the link. Okay. So this is the flow lah for those who are absent. So this is not just the flow. I mean, you need to do this. Okay. We have meeting yesterday. So this is compulsory to do like this. So up to you. You want to use mirror or you want to use second device, up to you. If you have laptop to see the question, you use it. Okay, but if you have Padlet, not Padlet, I mean iPad, or you have other devices like or if you want to use your phone also can. So we are seeing your phone lah. Okay. So the view will be, we see what you are doing. Okay, like this. Okay, right. Okay, now take 5. Hello. Okay, so I'm back. Okay, actually I want to do a little revision on the tutorial. Last tutorial, I didn't discuss on the Zenodiode question, right? Am I right? I just stopped until question for power supply, not Zenodiode, right? Am I right? Betul kan?
Yes, betul.
Okay, so today we'll do it sambung sikit lah. Okay, now the last one for the common base. Okay, for the common base, okay, the input is applied to the emitter. So this is how it looks like for the common base. Okay, so base now is grounded. Okay, base now is grounded. And then input now is emitter. Okay, output now is collector. Okay, so here you have RE at the input, at output you have RC. Okay, so for the RE, so the equivalent circuit, okay, so this is the hybrid pi model. Okay, since you have the collector, so let's write here. So this is emitter. So this is base now become ground and collector. Okay, the input is applied to the emitter. Okay, in this case, it has low input impedance, high output impedance, and current gain less than unity, and very high voltage gain. Okay, I forgot lah this one. For the common collector, it has high input impedance and the voltage gain is approximately equal to 1. Okay, after you derive this value voltage gain, you should get like 0.99 something. Okay, and okay, so that is for the common collector. This is for the common base. Okay, I pass all the example. We will look at the example next class. Okay, now it's just to derive it. Okay. Okay, after derive, make sure you understand, you do revision, okay, and then we do the example in the next class, okay? Okay, so the hybrid pi model, of course, we have GMV pi, okay? So the original hybrid pi model is like this, okay? Okay, R pi, and then you have here GMV pi, okay? And then you have here base, okay? Okay, base. Okay, so so when we draw it in different side, okay, in for the common base, okay, for the common base we draw it like this, where the GMV pi is going to the is from vertical to the horizontal, and then you have R pi. Okay, so now let's derive together. Okay, so in this case, so can you see what type of BJT is this? This NPN or PNP? Student, if you still remember, so this is BJT. Okay, BJT. This is base collector emitter. Okay, so for this one is NPN or PNP? The first one I draw,
PMP.
NPN.
NPN. Okay, NPN. So current from base to emitter is NPN, but when we have another one, okay, another one which is, sorry, I draw it a little bit down here, okay, but current, ayo, okay, so you have base, collector, this is emitter. So this one is NPN or PNP? So this one is PNP. As you can see, PNP current is from emitter to the base. How about this circuit? Is this NPN or PNP? Please
PNP.
carefully, please carefully see it. PNP or
PNP.
N? Yes,
PNP.
PNP. Okay. So most of the time for common base will be PNP circuit. Okay, PNP. Okay, so as you can see, so current now is going to the base and current IC is like that. Okay, that's why you have GMV pi going to the right. Okay, why? Because IC is actually your IC. GMV pi is actually represent your IC. Why? Because it is at collector node there, collector terminal. Okay. Okay, let's derive first. Okay. Okay, before derive, I need to draw it again. Okay. Okay, give me 1 minute. You know what is the best part of about common base? While writing this. So common base is as simple as common emitter without RE. So there will be no dem V test, I test. Okay. So I need to redraw it again. RE. Student, are you okay over there? Student,
Ya,
you
doktor.
all, are you
Yes,
okay
doctor.
over there? Don't worry, we derive it first, okay? Later in the next class, we do example together, okay? I hope you're all okay. Dad, don't be dad. I don't want to become famous. Doctors is Xylas students die because of AC equivalent circuit derivation. So I'll be the suspect. No, don't do that, okay? I hope you bertahan. Okay, so RC, this is V naught. Later I will become famous, okay? And all over the Malaysia gone viral. Okay, why the student die in Dr. Izaila's class? Because too much of derivation, isn't it? No, please don't. Okay, hang in there. Okay. All right. Okay, that's it for the VPI. So this is the base. This is, sorry, not the base. This is common base. So this is base, ground. This is collector and emitter. Okay, this is simpler than the other two Z tests. No Z test, whatever here. Okay, all right. Okay, let's do it. Okay, all right. So you have here I in. Oh, this is the circuit. Okay, so this is the circuit. So you have Z in is from RE. Okay, so this is your Z in. Okay, and then Z out is from RC. Okay, so this is your Z out. Okay, and then, all right, so this is your base. So this is base node. So this is emitter node. All right, okay, so, okay, that's it. All right, okay. Okay, that's it. I think that's it. Yeah, okay. So you have, actually here is I not. Okay, so let's do it. Okay, so Z in is equal to the RE. Okay, as you can see here. Okay, so this is the current here is IE. Okay, but then you have two node over here. So the current that flowing through the R pi is always IB. Okay, IB. So you have here current IE and you have here current IB. Okay, therefore it involved with two node lah basically. Okay, so you gonna have a new parameter here ZE, which is equal to the VE IE. Okay, VE over IE. Okay, so ZE first. Okay, ZE first. Okay, VE over IE. Okay, let's take a look here. So I nak buka chat. Is there any question in the chat or someone die? Not yet. Die. Oh, attendance. Attendance later, yeah? For those who late, you have to wait until finish, okay? So ZE, so VE is equal to what? Okay, VE at this node equal to what, student? VE from emitter to the ground. What is the voltage across VE?
Imply B pi.
Yes, correct. Thank you. At least someone alive over there. Okay, so V pi. How about IE? IE is equal to what? Can I just write IE is equal to the IB beta plus 1? Can I write like this? Can, right? Because what? Because I want to cancel out this V pi. Okay, usually I said V pi equal to what? IB R pi, and this one is IB beta plus 1. Therefore, you cancel out here, say you have here the portion is R pi beta plus 1. And finally, your Z in is equal to the RE parallel with ZE is equal to the RE parallel with R pi over beta plus 1. Okay, quite straightforward, this thing. Okay, and then Z out. Of course, okay, there is no other thing that is not logical. Okay, so you can straight away say that Z out is approximately equal to the RC. That's it. Okay, that's it. Okay, so now we've done for the part of the Z in and Z out. Okay, so this is the Z out. Okay, and make sure you know to derive the ZE. Okay, Z in is equal to the RE parallel with ZE. Okay, now let's derive for the AVOC. Okay, AVOC. Now, I think I will derive it here. Okay, AVOC. So AVOC will be, okay, AVOC. Okay, AVOC will be V out over V in. Okay, can someone give me what is V out? So this is without RL. Okay, therefore AVOC is equal to V out is equal to what, student? What will be the V out? Come on, you already know this. So V out is voltage across RC.
minus GMV pi RC.
Thank you for that. But is it minus? Look carefully over there. Where does the current GMV pi goes? It is to the right, right? It's going to the RC. Therefore, it is plus GMV pi RC. Okay, what will be your V in? Very straightforward over there.
V pi.
Yes, V pi. Correct. Thank you. Okay. Cancel out V pi. Therefore, GM RC. Easy. That's why I said common base is the most easiest. Okay. 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 Now, all right. Let's derive for the current gain. Okay, current gain. Okay. For the current gain, okay, so AI is equal to the I naught over I in. Okay. Okay, so how do you find that? You can actually do, since you have AVOC just now, you can say that we do like this, okay, AVOC, V in, okay, and then you have Z out, and then you have RL, okay, if you have RL, okay. All right, or you can actually do same like what you find in the circuit. Okay, so I out. So as you can see there, I out is equal to what?
Negative GMV pi.
Yes, correct. Thank you. Okay. Okay, so I out equal to the negative GM V pi. Okay, because it is in opposite direction. Okay, as you can see, so I out is the current across RC. Just now you find V out, you take the current GM V pi. It is the same current going through there. Okay, therefore, it is actually equal to the negative GM V phi. Okay, how about the I in? Okay, so for the I in, so we will draw the same thing like previous one. We will do current divider rule. Okay. May I know, do you have class after this? Sorry. What time now? Okay. I got time now. Okay. So this is your so like I said, so this is IE. So this is IB because this is emitter, this is base, and then you have I in over here. Okay, this is plus V in. Okay, so you know that your IE, okay, IE is equal to the RE, okay, use current divider rule, okay, over RE plus ZE, okay, I in, okay. So you know that IE is IB plus beta IB, okay. Because it is actually, IE is equal to the beta IB because IE is equal to this one lah actually. So IE is beta plus 1 IB, right? Okay, same thing. Okay, and equal to the RE over RE plus ZE, okay, and IE. Okay, so IB is equal to the RE, okay, over RE plus Z in, I in, okay. Then you have the portion over there of IB. Therefore, I naught So you replace here. So I naught is equal to the negative GM IB R pi because B pi equal to the IB R pi. So here you replace the IB over there, going to here. Finally, you will have the equation. Yes?
Madam, the 1 plus beta.
Hmm? Oh, I didn't finish it. Write it over there. Yeah. Should be. Lah. Thank you. Okay. Here. Thank you. Okay, now correct. Now correct, right? Okay. So blah 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 over there. Finally, okay, you plug in everything there. So therefore, I out over I in is negative GM R pi RE over beta plus 1 RE plus ZE. Okay. So this is for the AI, for the current gain. Okay, that's it for the derivation, for the voltage gain, input impedance, and also current gain. Okay, so do you have any question? Okay, so please take a look on the derivation. Okay, for the common collector and common base. Later, after test next week, we will do the example because I skip all the example here, but we will do next week. Okay, is it okay? Okay, please take a look after test. Take a look all the derivation again. Okay, so today actually I want to continue on the tutorial. Okay, okay. So why is not IE equal to the IV GMV pi? Okay, same. If you derive that, Irshad, okay. So GMV pi, it is actually equal to the IC just now, right? I said so. It is equal to the beta IB. So it is the same thing. IB plus. Do you get it? What I'm saying? Let me show you again. So Irshad said. So apa soalan Irsyad tadi? So Irsyad said why IE not equal to the IV plus GMV pi. So it is this actually the same thing. Okay, the same thing. All right, the same thing. So because I use so I use IE beta plus 1 IB. So actually you are right. IE is equal to IB plus GMV pi. But GMV pi is equal to IC. Doesn't it equal to the beta IB? So finally, you will get that it is equal to the IB plus beta IB. Same. Rishad?
Yes, Doctor.
Okay, are you clear
Yes, wow.
with that? All right, okay. Okay. Okay, so let's take a look on the this one just now. All right. So students, so I didn't explain this, but I think I better. Okay. Okay. So we stopped here last time. Okay, we stopped here. All right. Mm-hmm. Can you see my screen? Can you see my screen, student? Hello?
Yes, yes. Okay.
Yes, okay. Yeah, okay. So look at here. So I skipped this. Bukan, I don't have time the other day, but I think I have time like 5 minutes now. So determine. So what are the expected value of RL if the Zener diode is connected in opposite polarity? Okay. For example, in here. So what the expected value across RL? Okay, what the expected value across RL with the Zener diode, blah blah blah. Okay, so So now in this case, okay, in the original one, okay, so it is plus minus like that, can? Okay, so do you know that designer voltage you have here plus minus like that, can? So this one, if you connect your voltage like that, your power supply here plus minus, then your Zener diode will be regulate. Am I right? And then it will be reverse bias and it will be regulated. So now how about if you reverse it? Okay, this is the same like in the previous tutorial. How about if you reverse it? So current in this direction. So what happened to the Zener diode? So Zener diode will in forward bias, kan? It will not regulate, but it will be in forward bias region. Okay, so the question asks you voltage across RL. Okay, so Zener diode will be Zener will be in forward bias region. Okay, therefore, voltage across RL is equal to the voltage V forward if it is silicon 0.7 volt. Okay, same like the tutorial. Okay, in the tutorial last one. Okay, tutorial 1. Okay, determine the power dissipation of the Zener diode. Okay, determine the power dissipation of the Zener diode. So now we are looking back this one. Okay, the black one. Okay, plus minus on top. Okay, so how to determine the power dissipation? So meaning that you need to find your RS. So let's draw together. So in order for this, in order for you to define the voltage across whether this diode is Zener diode is regulate or not, how do you do? How did you do? So this is your circuit. Okay, this is your RL, this is your Zener diode. Okay, so this is your RL, sorry, what I cakap ni? Okay, alright, so this is 20 volt. So how to determine this VZ is regulate or not? How do you determine it? Still remember?
Yeah, we will find
Uh,
the VThevenin of RL.
yes, correct. Thank you. Okay, so this RL is equal to 1.5K. Sorry. Okay, so find VThevenin. Okay, which is equal to the 1.5K over 1.5K plus 330 times 20 equals to, for this case, can someone calculate for me? I don't have calculator now.
16.39.
Okay, 16.39 volt. Okay, therefore, when VThevenin, okay, VThevenin less than the, sorry, what is the voltage VZ given? Sorry, not less. So read the question. So VZ given is 12 volt. Okay, so given the IZ total, the 21 milliampere, and IZK minimum is 0.25 milliampere, and PZ max is 1 watt. Okay, given all that, therefore VThevenin is actually greater than the VZ given 12 volt. So what happened to the Zener diode? Is it regulate or not regulate?
It's
Regulate.
regular.
Yes. Okay, Zener diode regulates. Okay, Zener diode regulate. Okay, therefore, what will be the voltage across Zener diode? What value you take? You will take the value of 12 volt. Am I right? Yes,
Yeah.
12 volt. So here is 12 volt. So when you have VZ 12 volt, what will be the voltage across RL as well?
Will be
So
parallel 12 volt.
yes, 12 volt as well. Okay, so therefore VL is 12 volt. Okay, so now the question, go back to the question. They want power dissipation at the Zener diode. Okay, power dissipation at the Zener diode. So you need to find, so you have here is IS. So you have here So I need to redraw a little bit lower here. Okay, so this is Isaac. So this is IL. Okay, so can you find they want power dissipation at cyanide? So you need to find Isaac. Okay, in order to find Isaac, you need to find IS and as well as IL. Okay, so first, how to find IS, student? IS. How to find IS?
UCL.
Correct.
Yeah.
Okay, KVL first, okay? Because you know already the voltage drop over there is 12 volt. So can I straight away use like that? Can, right? Can, right? So can I say that that is across that KVL, therefore IS is equal to 20 minus 20 over 330? Can I say that? Can, right? So
Yes.
it is equal to the 24.24 milliampere. Okay, all right. Okay, so how about IL? So your objective is to find this IZ. Okay, how about IL? So IL is equal to what?
ZL over RL.
Okay, correct. So VL over RL, which is equal to the 12 over 1.5K. So you will get 8 milliampere. So you have these two values. So how to find Isaac at this particular KCL? So at this point, what is Isaac?
You will find as a KCL.
What is that? What is the equation for Isaac over there?
IS is equal to ID plus IL.
Okay, correct. So
IZ.
it is IS minus IL. Am I right?
Yeah.
Yes. Okay. So Isaac is equal to the IS minus IL. So IS you have calculated there, minus IL, which is 24.24 milli minus 8 milli. So you will get Isaac is 16.24 milliampere. Okay, so PZAC is equal to the Isaac VZAC. Okay, so in this case, you multiply 16.24 milli times VZ is 12. Therefore, this one you will get around 0.195 watt. Okay. Actually, I have given the answer, but then we better do it. Okay. All right. So that's it. Okay. So for the C part, okay, assume that the power supply voltage is equal to the 0 volt now. Okay. So now this voltage, okay, this voltage is okay, so this voltage is 0. Okay, at some point along the way, okay, the 12 volt diode will stop regulating. Okay, will stop regulating. Okay, so determine the supply voltage. Now they want to know the supply voltage, okay, where the regulation is lost. Okay, meaning that they want to know the minimum VS. Okay, they want to know the minimum VS, the minimum power supply that it could be lah. Okay, so to find the minimum, okay, you need to find, as you can see here, given the max and the minimum. All right, so this is the way actually. Okay, so to regulate, okay, in order to regulate your Isaac, okay, in order to regulate your Isaac must be in between this thing lah. Okay, the Isaac mean. Okay, and also the Isaac max given. Okay, so that is to make sure it is regulate. Okay, so now they want to know the minimum power supply. Okay, the minimum power supply. Okay, therefore, when you use minimum, therefore IS minimum. So in this case, you know that IS, okay, IS is equal to the Isaac plus IL. Okay, this KCL at this red node here, this one. Okay, so when you want minimum, therefore this will be minimum. Okay, Isaac also minimum. Okay, in this case, your IL is fixed just now because it is 12 volt voltage. Okay, so what will be your IS minimum? Okay, so IZ minimum, as you can see, it is given in the question. Okay, see, IZK is at knee voltage. It's like if you see the drawing, it is like this. So this is at forward bias and this is at reverse bias. So this one is this one is IZK. If you look at the current IV characteristic. So IZK is over there. Okay, therefore that is IZ minimum. Okay, so this is actually IZ minimum. Okay, which is 0.25. Okay, and IL you have calculated before, which is 8 milli. Okay, so this part you will get 8.25 milliampere. Okay, so for the VS minimum, okay, therefore at this KVL loop, okay, we know that VS, okay, if I write it again in the KVL loop, okay, so VS, okay, VS is KVL loop this one. So VS is actually IS RS plus VZ. Okay, when you have IS minimum, yeah. Okay, therefore this is you find your minimum VS plus VZ. Okay, so finally you will get this is equal to the 8.25 milli times RS is 330 plus 12, which is equal to the 14.72 volt. Okay, so this one, the minimum voltage is up to here only. Okay, so what is the minimum voltage? It is equal to the 14.72 volt. Okay, that's it. So if you expect that, so in your actually in your question later, so you're gonna have this kind of question. Okay, I mean in the test. Okay, there will be a question for this part Zener diode. All right. So do you have any question regarding this? Okay, remember that student. If you put this is so your key is this. Okay, so this is the key. Okay, at this particular node. Okay, at this particular node. Okay, when you put this minimum, when your IS minimum, therefore IZ mean minimum. But let's say if you have for example the question asks you the maximum, okay, the maximum, therefore this will be IS maximum equal to the IZ maximum plus IL. Okay. Yes. Okay. So if you the question one minimum, therefore it will be minimum. So the question one maximum, it will be maximum. So where does the IZ maximum you get? So IZ maximum you get is given here. Okay. IZ total here is IZ maximum. So sometimes in the textbook it will be written IZ M. Okay. IZ M. Okay. So it is IZ maximum. So IL in this case is fixed. Okay. Because it is equal to the 12 volt just now. All right, I think that's all for today. Thank you for waiting for me. Okay, so do you have any question? I show the slide first. Okay, so do you have any question, student? Hello?
No question, no question.
No question. Okay, great. Oh, yeah, this is the attendance. All right, if no question, thank you very much all. And good luck for the test this Friday. Okay, please be on time. Okay, we will gather together at 9 a.m. and do a short briefing and then do the attendance and so on. Okay, I hope that everyone can come on time at 9 and the WebEx. Okay, I will give the instruction, the link for submission by later today. Okay. All right. All. aside first the BJT. I hope you see there.
Doctor, can you show please again?
Okay, all. Bye. You may leave the
Doctor?
class.
Okay, thank you.
All right.
Thank you,
Okay,
doctor.
all. Okay.
Thank
Good
you,
luck.
doctor.
Okay. Please.
you, doctor.
Okay. Put aside the BJT first. Do revision for the test. But the test is simple, but you need to be careful. Okay. Please be careful on the calculation. Okay. Also, think first before you write. Okay. You definitely gonna have plenty of time to answer the part A and part B. Yeah. Sure. For that. Okay. See you on Friday. Bye all. Um,